Okay, in this video, we're going to prove out the trigonometric identity. And so we're going to do the angle sum formula of sine. And looking at this, this is going to be our strategy. Okay, so we want to start off with our general statement of sine of alpha plus beta. So we go sine alpha plus beta. And our general strategy is that we look at alpha plus beta right here, and the triangle that is going to, basically the right triangle that is going to encompass that is going to be this guy here, and that side, okay? And so we're going to start there, and I want a little bit of background, I'll give you a background of some informational lines that I drew in some of the side strategies that we're going to need. First of all is that this line right here, BE, is going to be a perpendicular line to AE, which is down here. This line right here, DF, is also perpendicular to line, well, basically the ray, I should say AE, okay? Then I drew a line right here, BD, that is perpendicular to line, or I should say ray AD, and then we have a line right here, CD, that is going to be perpendicular to the line that we drew, BE. So, lots of information, and this is going to be the slickest setup, and you'll see why that is. 2 bits of information that we're going to need to kind of like review is parallel lines and this business of alternate interior angles. So 2 parallel lines cut by a transversal are going to give us alternate interior angles that are going to be congruent, and similar right triangles. And so if we have a right triangle right here, and then we draw its altitude from the hypotenuse to the right angle, it splits up into these 2 triangles right here. Small triangle, and then of course the medium-sized triangle, which is right here, okay? And that's the way that they break down. So we're going to be using those angles later on, just to go ahead and connect some pieces. So I'm going to erase this out, and we'll start. Okay, so our first statement that is true that we want to say is that the sine of A, or should say alpha plus beta, is going to go ahead and equal BE over AB. So again, we have that triangle right here, okay, that angle I should say, and this is going to be the opposite over the hypotenuse, okay? So that's a true statement so far. So what we're going to do next is this. We're going to break BE into 2 segments, and so we're going to go ahead and we can see that BE equals BC plus CE. So we're going to break that up, and we'll go BC plus CE all over AB. And again, this is what we're talking about right here. Okay, notice that BE consists of those 2 line segments, and so I'm just busting those up. And so I'm creating basically 2 line segments that are going to form together to form 1 line segment. Next, I'm going to go and I'm going to take CE, which is right here, and since this guy, and I'll just show you real quick here, that this is a rectangle, okay? By definition, we got those, all 90-degree angles and whatnot, so that's going to be a rectangle. So that means is that I'm going to take CE and replace it with DF. So that's going to give me BC plus DF all over AB. And again, I am replacing this with this because they are of equal length. Next, I'm just going to go ahead and, even without referencing the diagram, I'm going to go BC all over AB plus DF over AB. Okay? And so, from here, we're going to have to, this is where things start to get tricky. So, this is where the properties that we're going to see on the right-hand side here, the parallel lines, come into effect. Okay? So we'd have parallel lines that are cut by a transversal. And so what I'm going to do is that I'm going to create, I'm going to go ahead and show an extension of the parallel lines here. All right, not my finest moment as far as drawing goes, but I want to make sure that we see the fact that these angles right here, alpha, is going to be congruent to this guy right here, okay? Using the fact that, again, if we have these two parallel lines right here, and it's cut by the transversal that's in the middle, alternate interior angles, so again, these are going to be congruent to one another. And now that I got that out of the way, using the diagram over here with the similar triangles, similar right triangles I should say, is that it says that this angle right here in the smaller triangle is going to be congruent to the smaller angle in the larger right triangle. So that means is that this right here is going to be congruent as well. So I'm going to call this is also alpha, okay? So it goes from here to here to here, okay? And so let's see how this works. Okay, so what I'm going to do is that if we notice this triangle right here, okay, and we're going to home in on this triangle because that's going to help us get some parts that we need. So it looks like if I were to make a statement about this triangle, and I'm trying to incorporate the adjacent side, okay, and I'm going to try and incorporate the hypotenuse here, which we know that that is going to be cosine. So it's fair to say that cosine of alpha is going to equal the adjacent side, BC, over BD. And if I multiply each side by BD, these are going to cancel out, and I end up with BC equals BD cosine of alpha. Okay, so how does that help us? Okay, so what we're going to do is that we're going to combine these two statements right here. So we're going to concentrate on this first part of the fraction, BC over AB. And we know that BC is going to equal this. So I'm going to substitute that in for BC right here and rewrite. So I'm going to get BD cosine alpha all over AB. Now, what's interesting about this is the following, is that if I look at this, we got a cosine alpha, and I notice I got, okay, well, that's part of what I'm trying to achieve up top in my proof there, okay? And I have BD over AB. So nicely enough, if we look at this, I have this over this, okay, in a right triangle. So it looks like if I take the sine of AB, right? And so I'm just going to write this right here. If I have the sine, and I should say the sine of beta, that is going to equal BD over AB. So, which is what I have down below. And so I'm going to transfer that in, and I'm going to get the sine of beta and the cosine of alpha. So it looks like I have this part ready to go as well. So halfway done. So let's see if we can go ahead and knock out the second part. Okay, so in this next part here, I like to cheat a little tiny bit, and I know that I need a cosine beta and I need a sine alpha. And if I look at the cosine of beta, I got beta right here, and cosine would be this side, right, over this side right here. And so that means is that I would need AD over AB. And to look at that, I'm just like, okay, well, how can I incorporate this? How can I get AD into the mix here? And it looks like I can get AD into the mix by, and I don't know why I'm saying into the mix, maybe because I think I'm cool, is that if I look at the sine of alpha, that's going to give me the opposite over the hypotenuse. So I might be able to use that information, the transfer AB on over, so I can start to put all the pieces together in a rewarding way. So let's start there with this business of the sine of alpha. Okay, so, oops, I put a theta there. That's no good. All right, so the sine of alpha equals df, right? So opposite over hypotenuse, AD, and there's the alpha right here. So what we can do with that is that down below, we can just do it right here. Multiply each side by AD, and those will cross out, and I'll end up with df equals AD sine alpha. Okay? And so that seems to go ahead and be some good stuff, because for the second part, since this is a df here, I could go ahead and try and substitute this in and see what shakes loose. I got a feeling we're going to like the results. And so here we go. Okay, so substituting that out for df, looks like this is what we have, and I end up with the other trig ratio there. And so let's see what this is going to be. So if I look over here, I can say the cosine of beta is going to equal adjacent over the hypotenuse here. And so therefore it's going to equal cosine beta equals AD over AB. And guess what? That's what we have right there. And so at the end of the day, we're going to get cosine beta times the sine of alpha. And now it looks like if I have, if I'm keeping track of the parts that I need, it looks like that I have them all. And so it appears that I have completed the process. So I'm going to take this and move it on over here. And so, though it's a plus sign, it's a little bit out of order, this shows how we can get to this, okay, from this, rather, to the actual proof. Ew, that was bad. To the actual proof down below, and proving all of this stuff out here, okay, just using this setup. So, again, just kind of a peekaboo into where upper division mathematics goes. It's an interesting place to start, and kind of like an elegant way to show a very kind of like a complex concept using, things in which we already knew, just haven't put them together to form a larger concept. So anyhow, that's how you do that, and thanks for watching.